Welcome friend, in the next lecture of calculus first, and we started our chapter sequence. In the last lecture we discussed squeeze theorem and problems based on the squeeze theorem. In the today's session we have to discuss some more theorem on the limit of the sequence, and also we have to prove one theorem, that is D'Alembert's ratio test for convergence, and we have to solve some problems on this test. So we start our theorem. So first theorem we will discuss. Let x is equal to xn be a sequence of real numbers converges to x, then the sequence mod xn of absolute values converges to mod x. That is, if x is equal to the limit n tends to infinity xn, then we have to prove mod x is equal to limit n tends to infinity mod xn. Okay, so we have to prove the theorems. What we have given? We have a sequence of real number xn, and this sequence is converges to x. So what we have to prove? The sequence of absolute values, that is the sequence mod xn converges to the mod x. That means what? X is limit of xn, then we have to show mod x is limit of a mod xn. So we have, so what is given? Given that x is equal to xn converges to x. Therefore what we can say? Therefore what we can write? Limit x n tends to infinity xn is equal to x, and therefore by the definition we can write, for every epsilon greater than 0 there exists a natural number k such that what we have to write? Such that what? Mod of xn minus x is less than epsilon for all n is greater than or equal to k. Just we write the definition of a limit of the sequence. Then what we have to use? Say this is equation number 1. Now we have to use the one equality. So we have what we have? If a and b are the two real numbers, then what we can say? Mod a minus mod b, it is less than or equal to mod of a minus b. This implies that mod xn minus x is less than or equal to mod xn minus x, and this is less than epsilon for all n is greater than or equal to k, from equation 1. So from equation 1 what we can write? This term is greater than or equal to the mod of xn minus x by using this inequality, and therefore Therefore what we can write, mod of mod xn minus mod x is less than epsilon for all n is greater than or equal to k. But epsilon is arbitrary. Hence limit of sequence mod xn is equal to mod x. Is it? And therefore what we can say, that the sequence mod xn of absolute values converges to mod x. So very simple proof is there. Just you have to use the one inequality. It's very simple. Just write the definition for limit of the sequence and use this inequality. You will get this mod of mod xn minus mod x is less than xn minus x, which is less than epsilon. Therefore this is the we are getting, and this is nothing but the definition of a limit of the sequence, and therefore we are getting the sequence of absolute number is converges to the absolute limit. Is it? So similarly you can prove one theorem. You have to prove, this is for homework. Suppose x is equal to xn is a sequence of a real number and this converges to x. This sequence is converges to x, and this xn is greater than or equal to 0. That is, this sequence is sequence of a non-negative number. Then what we can say, that then the sequence suppose this is y, the sequence root xn, this converges to the root x. This sequence root xn converges to the root x. That is, what is homework? You have to prove this theorem. For homework, x is equal to xn is a sequence of a non-negative numbers which converges to the x. Then use this definition and we have to prove the sequence y is equal to limit xn root xn, y is equal to square root of xn converges to the root x. So in the similar way you have to prove this. You can prove this easily. Now we prove next theorem, that is D'Alembert's test for convergence of a sequence. Here what we have given, let x is equal to xn be a sequence of a positive real numbers such that limit xn plus 1 upon xn is equal to L is exists. If L is less than 1, then x is equal to xn converges, then this sequence must be convergence and this limit is 0. Okay, so what we have given that? Given that x is equal to xn be a sequence of positive real numbers. Hence what we can write, L must be greater than or equal to 0. Also we have what we have, also we have mod of limit n tends to infinity, this xn plus 1 upon xn is equal to L. We have given this limit is equal to L. So what we can assume, say this is star. Okay, so let R be a real number such that what we can write, L is less than R is strictly less than 1. And what it implies, that this implies that R minus L is greater than 0. So we can take this epsilon. Therefore from star, so use the definition from star for every epsilon greater than 0, take epsilon is equal to what? Epsilon is equal to, take epsilon is equal to r minus L. There exists a natural number k such that mod of xn plus 1 upon xn minus L is less than epsilon for all n is greater than or equal to k. Just we write the definition for the limit of the sequence. Okay, so what we can write here, just use the some properties of absolute function. So what we can write, minus epsilon is less than xn plus 1 upon xn minus L is less than epsilon for all n greater than or equal to k. Again you can add L in all sides, so L minus epsilon is less than xn plus 1 upon xn minus L get plus, minus L plus L get 0. So this is less than L plus epsilon for all n is greater than or equal to k. That is, so just consider these two terms, xn plus 1 upon xn is less than L plus epsilon, and what we have taken epsilon is r minus L. R minus L get cancelled and this is equal to R for all n greater than or equal to k. That is what we can write, xn plus 1 upon xn plus 1 upon xn is strictly less than what? What is remaining only here? R for all n is greater than or equal to k. And this implies that what we can write, all these both the terms are positive, therefore we can write xn plus 1 is less than xn r for all n is greater than or equal to k. Similarly, we obtain xn is less than xn minus 1 r. Xn minus 1 is less than xn minus 2 r and so on. That is, if you replace n plus 1 by n, then you are getting all the terms. Thus we obtain. So what we can obtain, if you put all those values, suppose you put xn here, so what we are getting here, xn minus 1 r. So what we are getting, we obtain this xn plus 1 is less than xn r, and if you put this value here, xn value, xn minus 1, this r into r is r square. Again if you put xn minus 1 value here, then what we are getting, xn minus 2 r into r square is r cube and so on. The similar way we are obtaining like this. So here if you write, it is for rth term, xk is into what we can write, xk r raised to n minus k plus 1, n minus k plus 1. Okay, and this implies that xn plus 1 is strictly less than xk r upon r raised to k. Here r raised to k is in the denominator, so this should be n plus 1. So n plus 1, xn plus 1 is less than xk r raised to n plus 1 upon r raised to k. If we say it, what we have to say it here, this term is for all n is greater than or equal to k. Okay, this is for all n is greater than or equal to k. Okay, so what we can write here, if you say this term, that is C is equal to xk upon r raised to k, we get. So what we are getting? Xn plus 1. Xn plus 1 is less than C into r raised to n plus 1 for all n is greater than or equal to k. For all n is greater than or equal to k. And what is our r? What is your r? What we have, r is in between 0 to 1. Is it? But we have if 0 is less than r is less than 1, then the limit of the sequence r raised to n, this limit is equal to what? 0. This limit is equal to 0. And this implies that what we can write here? Therefore, limit, if you take limit of the both side, so x n plus 1 n tends to infinity is less than c into limit n tends to infinity r raised to n plus 1. So what we can write here? This limit is limit n tends to infinity xn plus 1 is less than, this limit is 0, so it should be 0. And all these xn's are positive, therefore we can say 0 is less than n tends to infinity, xn plus 1 is less than 0. Therefore, by squeeze theorem, what we can say? Therefore, limit n tends to infinity, xn plus 1 is equal to 0. And that is what? Limit n tends to infinity, xn is equal to 0. And this is our target, that is limit of xn is 0. And therefore we can write, therefore this sequence x is equal to xn converges to 0. Okay, so you have to use some definition of limit and some calculations you have to do, or some assumption you have to do. Then you can prove it very easily. Now we take one example on the D'Alembert's ratio test for the convergence of a sequence. Now given that, what we have given that xn is equal to n upon 2 raised to n. Okay, and this n must be belongs to the what? It is must belongs to the natural number. This is a sequence of positive real numbers. Is it? Therefore, we use what we have to use? D'Alembert's ratio test. Okay, so what we have to find? First we have to find xn plus 1 upon xn. So xn plus 1 means what? Just replace this n by n plus 1. So what should be this? N plus 1 upon 2 raised to n plus 1. In the denominator is xn, so write down it is n upon 2 raised to n. Just do the simplification, n plus 1 upon 2 raised to n plus 1, and its reciprocal you have to write 2 raised to n into n. Is it? And now what we are getting here? This 2 raised to n can be written, it is in the form of 2 raised to n into 2 into what? 2 raised to n upon n. This 2 raised to n get cancelled, and therefore we have 1 upon 2 n plus 1 upon n. and this can be written, it is in the form of 1 by 2. Give the denominator to both the term, n upon n is 1 plus 1 upon n, and now try to find the limit. Limit n tends to infinity, xn plus 1 upon xn, it is equal to, this limit must be what? Limit, this half is constant, n tends to infinity, 1 plus 1 upon n. So this is equal to 1 upon 2 into 1 plus 0, and it is equal to half. And this is our L, and this is less than 1. And thus what we can say that by using D'Alembert's ratio test, what we can say that thus L less than 1, hence by D'Alembert's ratio test, the given the sequence x is equal to n upon 2 raised to n is convergent, and it is convergent, and what we can say, limit n tends to infinity, xn is equal to 0. Okay, that is we can say that limit, that is n upon 2 raised to n is converges to 0. Very simple. N upon 2 raised to n is converges to 0. Just you have to find this ratio, take limit. If this limit is less than 1, then directly by D'Alembert's test we can say that this given sequence is convergent and this limit is 1. So we can solve so many problems like this. So we solve some more problems on the sequence. So what is first problem? Show that 2 raised to n is not convergent, that is the sequence 2 raised to n. So we solve first problem. Let xn is equal to 2 raised to n. And what we have? We have 2 raised to n is always greater than n for all n belongs to the natural number. And what we have also, we have know that, what we know that the sequence n is unbounded. Hence what we can write, the sequence 2 raised to n is unbounded. Is it? And we know that what we know that we have a theorem, every convergent sequence is bounded. Is it? Every convergent sequence is bounded. But what we have? But 2 raised to n is unbounded. Therefore, by this theorem, what we can say? This 2 raised to n must be divergent. It is not bounded, so it is not a convergent. Is it? If it is bounded, then we are going for the convergence or not. But every convergent sequence is a bounded. Therefore, this sequence is not bounded. Therefore, directly we can say that this sequence is not a convergent sequence. Is it? So, this is the one problem. Second problem is what? Give an example of two divergent sequences such that their sum is convergent and their product is converges. We have to give the two examples of a sequences. So we write a solution second. So you have to give the two examples, or you have to give the example of two divergent sequences such that they are what? Divergent, and their sum and their product is convergence. Suppose x is equal to 0, 1, 0, 1 and so on, and y is equal to what? 1, 0, 1, 0, 1, 0 and so on. Now x and y is convergent or divergent? We see that what? X and y are divergent. They are divergent, or they are divergent sequence. Is it alternate sequences? They are not convergence. But, or we can say this implies that x plus y is equal to what? Addition 1, 1, 1, 1 and so on. And we see that x plus y is convergent to 1. This is converges to 1. It is constant sequence, therefore it must be converges to 1. Also what? X into y. S into y means what? This is nothing but xn into yn. That is just take a product. 0 into 1 is 0. 0 into 0 is 0 and 0, 0, 0 is this is a constant sequence 0, and therefore x into y converges to. Therefore what we are writing, x is equal to 1 0 0 1 0 1 0 1 0 1, y is equal to 1 0 1 0 1 0 1 0. Alternate sequences, both are not convergent, but if you take addition 0 plus 1, 1 plus 0, 0 plus 1 and so on, you are getting a 1 1 constant sequence. This is always convergent. Similarly for product. In a similar way you can solve so many problems. We will take in the next lecture monotone sequence and theorems on the monotone sequence. So thank you very much.